Welcome, everyone. I appreciate you guys taking the time out of your day to attend this webinar. Um, Today's webinar is a non-technical discussion. We will touch on some basic chemistry, some basic physics, but the overall goal of today's discussion is to really help everyone understand the properties of quartz that make it special and allow Quartzstein to utilize it as a precision sensor. So the idea around this webinar really came up from a number of trade shows that I've attended over my time working for Quartzstein. On some of these trade shows, we'd bring a rather large quartz ingot, and there's a picture in this webinar of large ingots, so you'll get to see one. And from that, what we discovered is a lot of people would come by just drawn to this large ingot, and they would ask a number of questions. And one of the first questions that they would ask is, why quartz? What's special about this rock that allows you guys to use it as a sensor? And another question, which we'll get to, is this natural? Is this real? It certainly is real, but we'll also answer that question as well, whether or not we use natural or synthetic quartz. So, but to add to, I guess, a certain level of credibility, let me introduce myself. Let's see. There we go. My name is Ryan Roush. I have a background in electrical engineering. I was educated at the University of Utah. I received my MBA from a local liberal arts college here called Westminster College. And prior to working for Quartzstein, I worked with precision instrumentation at Northrop Grumman, mainly for navigation instruments in the military, and then moved over to Quartzstein when I joined. I joined as the lead electrical engineer when we were structured more functionally, and then was promoted to the director of engineering back in 2015. And if you haven't seen, we had another leadership change or rotation that was just recently announced. As of March, I moved into the director of product line management, and the previous occupant, who was Jason Blackburn, he moved into the director of sales, and then the director of sales moved into the director of engineering. So we did a rotation on our senior leadership team. And the primary goal of that rotation was to ensure that we get a very well-rounded management team. Also, all of us really love Quartzstein, and we want to stay there. So it gives us unique experiences for growth and allows us to keep adding to Quartzstein and contributing in a very valuable way. So I've been around. I'm not a quartz expert. We have a PhD scientist who's our quartz expert, and I collaborated with him quite a bit on this presentation, but I've had a lot of exposure to quartz and our quartz processing line. So to go over the things that we're going to cover today, we're going to go over Quartzstein's background. We have a number of people on this webinar that are not uniquely familiar with Quartzstein, meaning that they're not customers, but they're interested in quartz. So just to go over, our brief history and some of the capabilities that we have. Then we're going to get to what is quartz. We'll answer the question versus lab-grown synthetic quartz or natural. We'll talk about where quartz is used. A lot of people aren't familiar with how quartz actually is touching almost every industry or every technical industry. And then we'll really get into the meat or the heart of the message, which is the properties of quartz in relation to a sensor. And we'll touch on things like hardness, the magic piezoelectric effect. We'll touch on energy loss, elasticity, and then there's a few more in there as well. And then we'll wrap up with a brief summary. And at that time afterward, I'd like to open it up to Q&A. And if there's any questions, hopefully I'll be able to answer them. And if not, right off the bat, I won't try to answer something I'm not an expert in, but I certainly can guarantee you we can get you an answer. So let's jump right in. So to get into Quartzstein's background. So Quartzstein has quite a long history. The company itself has been around for 30 years, but our storied history actually goes all the way back to Dr. Errol Ernest and his research at Sandia, working with the Department of Energy with quartz and doing research on quartz as a sensor. And so, when he left the Sandia National Labs back in 1979, he relocated, and luckily he chose Salt Lake City, Utah as a place to set up shop. And in 1979, Quartzstein wasn't around, but there was a group of individuals that were very interested in shaping quartz and using quartz as sensors and finding applications for quartz. And so these sensors consisted of accelerometers, weight sensors, pressures, clocks, temperature sensors, force sensors. And during this decade, there was an opportunity that was presented to this group to come up and design and build a clock using a quartz sensor. That's actually one of these 3 stacked crystals right here in the top right. And that opportunity was presented. They accomplished that and met the specifications. They were displaying it, and a well service company observed the application because it was on a public display and said, if you can do that with a quartz sensor, maybe you can create a pressure sensor. And so, from that challenge, this group of individuals stepped up and they worked and created a pressure sensor, which is the middle sensor there. And they handed over that design to that group because they were primarily a research and development organization, and that was their goal. And in short time frame, there was 2 paths that were taken. One of them internally, which was, Dr. Ernest could see many improvements that could be made upon the design. And he started, thinking and testing and working towards that. In addition, the company that inherited or purchased that design, they ran into a number of manufacturing problems that prohibited them from moving forward. And so they came back, and around that time, I'm not sure which one occurred first, but they said, hey, it'd be a lot better if you guys could make this for us. And out of that was born what we'd refer to as the quartz butt joint sensor, which is the 3rd sensor. This is the heart of a Quartzstein transducer. And from that time onward, so this is about the early 90s, 1990, Quartzstein shifted its focus from primarily a research and development house that was out for hire to a manufacturing company. And from that point on, they were manufacturing quartz pressure transducers used primarily in the oil and gas business. That's the niche. In 1998, we were acquired by the Dover Corporation, and we were owned by Dover up until their spinoff in May of 2018 into Apergy. Many improvements have been made to the quartz pressure transducer, and that's probably another webinar altogether. But some notable, facts: we moved from surface mount technology to hybrid technology. This is a hybrid right here, and have some strong capabilities there. In 2019, we started offering a piezo gauge, and again, the specifics of the piezo gauge are probably another webinar in and of itself. But it's inherently different from the quartz transducer. There's some unique properties there, but primarily our business is manufacturing the world's best quartz pressure transducer for the oil and gas industry. So some of the capabilities that we have at Quartzstein to lend to our credibility to speak about quartz is we have a whole quartz processing facility where we take in raw quartz. This picture in the left column is what we affectionately refer to as a Jolly Rancher. And so we receive this subassembly and we test it, we shape it, we grind it, we plate to it. Overall, and you'll see in a slide, we take this piece of quartz and we change it into a precision sensor. In addition to that, we have resonator mounting capability and cold welding capability, things that are important in order to ensure that the quartz has a very high Q, which we'll talk about a little bit later in the presentation. In addition to the quartz processing capability, we also have hybrid manufacturing capabilities. We design our own custom microchips at Quartzstein. We have the ability to program those. We have the ability to manufacture hybrid packages. We do both gold and aluminum wedge bonding. We have the ability to hermetically seal via welding method these packages, and we do this and the quartz processing, or we call it the sensor lab, in a class 10,000 clean room. In addition to that, we have, it's a made-up word, but it's a word that I like, electromechanical assembly. So we can take this precious electronic jewelry and we can ruggedize it by placing it inside of very strong and robust metal housings. We have the ability for HMP soldering. We do our own in-house e-beam welding. We have actually a second e-beam welder that will be coming online this year. We do our own shock and vibe testing. We design our own electrical testing. We also have a RoHS assembly line and our ISO 9001 50,000 square foot facility. And the most important part, because ultimately I think what sets us apart from other sensor manufacturers is our accuracy, is we have a world NIST traceable calibration facility. In order to calibrate our quartz pressure transducers to the accuracy required, we can hold our temperature stability within 1/10 of a degree C in these very large oil baths, and that's going to temperatures up to 225 C. And we dwell there for long periods of time to increase the stability and accuracy of the data that we recover. And so all of this is under one roof in our facility in Salt Lake City. And we have an incredible staff of individuals that lend their expertise into producing these products for our customers, which we're very happy to do. So enough about Quartzstein. Let's talk about quartz. So, what is quartz? On the screen here is a picture of what rockhounds affectionately call rock crystal. The Greeks actually referred to pieces of quartz like this as crystallos. They believed that the gods had actually somehow frozen water that was warm because it wasn't cold like ice. And so they were unsure exactly what it was, but they believed that it contained magical properties. Quartz actually, you could say, we understand the science behind it, but you could absolutely refer to it as containing some magical properties. We'll talk about that. But quartz in and of itself is just silicon and oxygen. Its chemical makeup is very similar to glass. It's a silicon dioxide. Now, when it's structured in its crystal lattice, it's actually, and you look at it more from, I guess, what they would call a Lewis structure. So you've got silicon in the middle, and it's surrounded by oxygen atoms, much like in the top right hand part of this display. If you were to look at that crystal lattice, you could actually refer to it as SiO4. But quartz is the second most abundant mineral on the earth. You can think of quartz in your life. You probably are very familiar. If you own a home, you might have had the choice of countertops. So you're going to have quartz or granite or whatever stone that you might be looking at. That's a little bit different quartz than what we're talking about. So quartz comes in many different varieties. Those quartz granitops are a polycrystalline quartz. The type of quartz that is required or needed for precision sensing elements is a single crystal alpha quartz. And so what you're looking at is within the crystal structure, it is all one single crystal that has been grown, where a polycrystalline quartz is a bunch of quartz that is mashed together, and so it's not one single crystal. And so there's some different properties when you're working with a single crystal alpha quartz for sensors than you have for a polycrystalline quartz or any other type of quartz. It's important to note that within nature, there's many common varieties of stones and precious gems that are quartz. Amethyst, which is the birthstone for February is actually a type of quartz. It's a quartz, I believe, that's been subjugated to high temperatures, which gives it its purple color. And then you also have rose quartz. I was just recently on a trip, an international trip down in Argentina, and that's a type of quartz that's very abundant in that country, and they shape it and sell it and use it in their jewelry. So, you know, using quartz as an electronic instrument, really most of that quartz historically came from Brazil. And what drove the demand and the need for that quartz was the war effort and the military-industrial complex. And you know, this picture in the lower right shows prior to the development of synthetic quartz. By the time those quartz crystals were, you know, inspected, shaped, plated, they were far more expensive than pure gold. Because, you know, pure quartz has, you know, imperfections and anomalies and can contain actual liquids or oils inside of them. And so, you know, all of that had to be, you know, more or less shaped around when using for a crystal application for electronics. And so this is a example from a historical video that shows an inspection that was taking place, and they were deciding where on the quartz they could actually use and where is scrap, or what wouldn't be able to be used for a quartz resonator. And so they knew, based on the need for quartz and an increased demand for accuracy, there had to be a better way. And so that's really where synthetic quartz, which is what Quartzstein uses to develop and shape for their sensors. So we do not use natural quartz. But back in the 1950s, the better way was investigated and engineered. And so the way this process works, which is actually a marvel of modern engineering, is that seed quartz, which is a thin plate of quartz, is placed between two electrodes. And then that is placed inside of an autoclave at very high temperatures and very high pressures. And there's a temperature differential in this autoclave. And over long periods of time, 35 to 40 days, large synthetic ingots are grown by the raw quartz crystal, the natural quartz crystal at the bottom, then depositing quartz at the top on these on the seed quartz. And what comes out of it are these 8 kilogram large quartz crystal ingots. And this is what I was talking about at the first of the presentation, these large ingots. This is what we would bring to a trade show and put out on a table that people would pass by. Sometimes when we're going international, we'll bring smaller ones like this one here that could be seen. And if you're ever at a trade show and you see that out on the table, please come over and take a moment. You can actually look in the center. You can actually see the seed between the two electrodes. But it takes quite a bit of time for this to occur. These are growing around 0.5 millimeter per day. And so it takes quite a bit of time for that to actually occur, for it to then to be harvested and used. But it's done in a very large batch process. And some of the incredible benefits is you don't have to go through that process of inspecting and scrapping based off natural anomalies that occur in the crystal. It provides easier handling. When the purity that you're getting, you can then have setups and you can dissect these crystal ingots more or less without having to do custom setups each time, like what was needed to be done when you were using natural quartz. And so, these quartz ingots then are broken down and they're shaped into quartz bars. And then those bars are broken down into blanks, and that's some of the product that Quartzstein receives and then does further processing in order to make our quartz pressure sensors. So quartz applications, obviously, if you're attending this, you understand that we utilize quartz as our pressure sensor, but where else is quartz used? Quartz actually is referred to as the salt of industry, or used to be referred to as the salt of industry. I would say silicon has probably taken over as the salt of industry, but quartz crystals are used in almost every technology. Military, lab metrology, industrial, consumer products, automotive. Obviously we're pretty familiar, and we'll talk just a little bit more about quartz inside of wristwatches. But almost every piece of electronics contains a quartz clock. And the computer uses that clock in order to, for timing. And so, depending upon the application, you can require a very accurate quartz clock, much like we have very accurate quartz pressure sensors, or you can have, like on a wristwatch, which is a much less accurate, although far more accurate than a mechanical wristwatch. It's far less accurate than a quartz oscillator that would be used in a lab or a metrology application. So guaranteed, even if you didn't know it, all the products that you interact with, they all contain on them, at least somewhere on their circuit boards, a quartz clock. And so this begs the question, well, what does it look like? And so that's a great question. So in the center here is a picture of canned quartz oscillators. And on the left, this is something that I think we're mostly familiar with, which is the quartz oscillator that is in a wristwatch. And so the frequency at which a quartz tuning fork is vibrating inside of a wristwatch is 32,768 hertz, or it's vibrating at 32,768 times a second. So a hertz is just a vibration per second, or a movement per second. And so that wristwatch is specifically designed and tuned in order to be at 2 to the power of 15. And then that is utilized in order to break down and power this wristwatch, which is far more accurate than a mechanical watch. A wristwatch using quartz may lose 1 to 3 seconds every month, which is far better than a mechanical wristwatch, which may lose 1 to 3 seconds every week. One of the things that's interesting about a quartz wristwatch, which is also interesting about quartz oscillators, depending upon the cut of quartz, which we'll get into in just a moment, the wristwatch is designed to be at a specific temperature. And so if you utilize your wristwatch at very high temperatures, like say you're a soldier and you're deployed to Iraq, you're going to have different loss of time on your watch than you would be at an ambient temperature, which would be, let's say, 72 degrees. And if you're deployed into Alaska and you're out on patrols for long periods of time for a month, again, you're going to see your clock be a lot less accurate than it would be if you're ambient temperature. So one thing to note is that quartz is subject to the force of temperature, and that affects the accuracy. And so it's a variable that needs to be designed for. But quartz oscillators are packaged hermetically inside of these packages and then mounted directly on circuit boards or using through-hole type componentry. And this is an example of a lid that has been carved off. And you can see this type of resonator, which is different than this tuning fork type of resonator. This is a bulk thickness resonator. And this is the same type of resonator, not the same exact type, but the same type of resonator that Quartzstein uses inside of its pressure crystal. And it is powered or energized by a microchip here, or oscillated is the word we use. Where this tuning fork, it's more fragile, meaning that you can damage or break the tuning fork. And so even though it's packaged in this metal can, it is fragile, where these thickness shear mode ones are more robust, more ruggedized. And so you'll know some watches actually advertise G-Shock is a term that you can see. They package this quartz sensor in order so that it can take far more shock than a normal or regular watch. But this is what they look like. These type of devices are mounted and put on almost all electronic boards, unless accuracy is not as important. And then some people now are using silicon clocks instead. But again, they're a lot less accurate. Quartz oscillators, bulk oscillators like this, they can range anywhere from 1,000 kilohertz, or 1 kilohertz, so 1,000 times a second that it's resonating, up to 500 megahertz. So that means it's moving 500 million times every single second. And so those are bulk devices. There's also devices that use acoustics with quartz. They're called SAW devices. And those are for very high frequency communications. And those are 150 megahertz to 1.5 gigahertz. And so much higher frequency. Those are moving at many more times a second. And so, a lot of times people are blown away that you could have a device such as, this crystal oscillator right here that could be moving 500 million times a second. And we'll talk about how that happens and why that can occur. That is subject to the material and some of the magic of quartz. So let's get into the properties of quartz now. So one of the first properties of quartz that is incredibly important and allows us to do what we want with quartz is that it is chemically inert. So again, looking at the structure of quartz, it's silicon dioxide. You look at the Lewis structure. You've got these bonds that want to form with the silicon and the oxygen. And what happens in a Lewis structure when it's silicon dioxide is you have a silicon in the center, and then it's surrounded with 2 oxygen molecules. And they are bonded together with 2 covalent bonds. And the takeaway here, from a physical chemistry standpoint, is covalent bonds are incredibly strong. And when you get around more oxygen, you're actually building a crystal structure. Those 2 covalent bonds will actually be shared with 2 other oxygen crystals. And that's what allows this tetrahedron to form. And the reason why the tetrahedron is so important when it comes to the quartz structure is because once the tetrahedron forms in the angular formation, which is this picture right down here, the takeaway from that is quartz is incredibly happy being quartz. It doesn't want to react with other elements. It's very stable at that point. The atomic structure is incredibly similar to diamond. That's why there's some properties that are very similar. But the key element, or the key, no pun intended there, the key point is that quartz is a molecular crystal because you're using multiple elements in order to formulate a crystal, where diamond is an elemental crystal. And so it's going to be much stronger. It's pure carbon, where quartz is silicon and oxygen. But both have incredibly high melting points. They're non-soluble. There is an exception, like all things. Quartz is incredibly happy being quartz. But the one thing that is different is, or the one exception to that, is quartz is subject to fluoride etchants. So like glass, other silicon dioxide, you can use hydrofluoric acid in order to etch quartz. And hydrofluoric acid is extremely dangerous. If it gets on your skin, you won't feel it until it actually gets to your bone, at which point it will actually start reacting with the calcium in your bone, and it's incredibly painful. But it is one method in order to remove quartz at a molecular level. Fluoride etchants can be used. And so the key takeaway from this slide is that due to the atomic structure of quartz, it is incredibly inert to almost all other elements and substances besides hydrofluoric acid, but it can be surrounded by other chemicals and not react. It's very stable. Property number 2. So quartz is incredibly hard. It's a 7 on the Mohs scale of hardness. If you're a rock hound, you may be familiar with that scale. That's not one that I actually am that familiar with. And so I think an absolute hardness scale may be a better way to talk about it. And so that's why I've included this graph from the GIA Institute. Something like talc powder is a 1 on the absolute hardness scale. Quartz is 100. So it's 2 orders of magnitude stronger than talc. Diamond is 1600. So that diamond on the absolute scale is a 1600, quartz is 100, and then talc powder is a 1. And to show you kind of the difference. But quartz is a hard substance to work with. It requires diligent preventative maintenance on our equipment. In order to keep any type of dust or particulate matter out of the air and ensure the safety of our workforce when working with quartz, we use wet processes instead of dry processes. That also helps us keep the heat down when working with it. And so this illustration here is on the very left-hand side is the Jolly Rancher. I referred to that earlier. So it's a piece of quartz. And when we get these in, we do some inspection to ensure that the properties of the quartz meet our quality standards. And then we actually start utilizing the equipment in order to shape it. And like I spoke to earlier, we have to be very diligent in our facility on keeping the equipment that actually grinds and removes quartz away from the Jolly Rancher up to date in certain hardnesses and sharpnesses in order to make sure that it's not trying to remove any material like dull. And so we have experts in a type of science that I wasn't familiar with till I came to Quartzstein, which is tribology, the study and of the science of friction and how substances wear and move against other substances. And that's an important science understanding that we have in order to utilize some of the properties of quartz that are important for sensing. Because if you were just to try to create these type of shapes using hydrofluoric acid or using a chisel and a hammer, you wouldn't be able to get the precision that's required in order to harness the accuracy that's needed in the sensor. So I'll move to the next property here. So property number 3 is really the magic of quartz, which sets it apart and allows it to be utilized as a sensor. So we're talking about the piezoelectric effect. So back in 1880, the Curie brothers, famous scientists, discovered that when they squoze a piece of quartz, they squeezed it, added pressure to it, that they were able to record an instantaneous charge. And that charge was in magnitude of how hard they were able to squeeze it. And so that is a specific property of quartz that is unique. This doesn't happen in glass. There are other piezoelectric substances, but quartz is a special one that also has hardness and chemical inertness and some other properties that we'll talk about later that allow us to harness this. And so what's interesting is you probably have actually utilized in your life this piezoelectric effect for your benefit. And many people, if you've ever turned on a gas stove or turned on a barbecue or used a cigarette lighter, you're using, if it's not the flint and steel type, you're utilizing the piezoelectric effect, which means there's a mass that's pulled back and then a spring launches that mass against a piece of quartz. And it happens that the quartz is shaped such that it actually produces a spark. That charge is large enough that it arcs. And when subjugated, that arc around a flammable material, it will create a flame. And so the way that this is done is when mechanical stress is applied to that crystal structure, a charge imbalance is created. And when a charge imbalance is created, it has to go somewhere. And so it actually can create a voltage that's measurable. Quartz-9, we don't utilize the piezoelectric effect. We utilize the inverse piezoelectric effect. So what we're doing is what's on the right-hand side. We actually induce a voltage. And so we create a charge imbalance in the crystal lattice. And by doing so, we actually physically cause the quartz to move. And so our quartz resonator, we have electrodes on the outside of our pressure crystal, and then we input a signal that actually causes that to move at 7.2 million times a second. And then what we're doing, we're measuring that movement. We're recording that frequency. And when we pressurize our crystal, that frequency shifts. And we look at that difference to the pressure crystal versus a reference crystal. And that's how we're able to determine with such accuracy what the pressure is. But it all happens due to the magic of the piezoelectric effect. Without that, we wouldn't be able to determine with such accuracy what the pressure is downhole. Other companies use the piezoelectric effect in order to sense vibration. And so that's more of an instantaneous, like accelerometer application. So if you've ever done any type of field engineering or test engineering, you'll usually mount an accelerometer on whatever you're subjugating to a vibration or a shock. And then you're able to record because when that shock or mechanical stress occurs on the device, you can then pick it up off of the quartz crystal and diagnose and find out what the magnitude of that stress was. And so that's another application. There are a lot of different companies that manufacture those type of quartz accelerometers, but they're using the piezoelectric effect, where Quartz-9 exclusively uses the inverse piezoelectric effect. So this next property, it's a little bit mind-boggling. So most people are familiar with isotropic materials. And isotropic is a word that means that the properties of whatever the material is are not dependent on the orientation. And so some easy materials that we're familiar with, glass or metals. If you have a cube of steel, it doesn't matter the orientation of the cube, the properties of that steel are all the same, regardless of the orientation. Now, it's different for quartz. Another material, maybe to explain this property a little bit further, it's also anisotropic is the word used to describe something that is dependent on orientation. Wood is an anisotropic material. So if you've ever worked in a wood shop or taken junior high shop, you'll know that wood has specific strength properties that are different depending upon the grain. And so you change the orientation and you've changed the strain or the strength of that wood. And so that's an example of an anisotropic material. Quartz is an anisotropic material, very much so. So quartz, depending upon the orientation, has very different thermal coefficients of expansions. And so we talked about, earlier in the presentation, we talked about the watch crystal. And so a watch crystal uses a cut of quartz. And when I refer to a cut of quartz, what I'm referring to is the orientation of the quartz crystal. So this is one of the magical things about quartz, is depending upon how you cut that crystal and the angles at which you cut it, you're going to harness different properties for different applications. And so one of those properties is sensitivity to temperature. And so the XY cut, that's what it's referred to, is the cut that's used for a watch crystal. And that happens to be sensitive to temperature. It's cut in a way that it is most linear, meaning less sensitive in the ambient range, but it is sensitive on those extrema, the cold of Alaska or the heat of the desert, and it will lose accuracy. So knowing that and understanding, one of the things that Quartz-9 does is, we have a temperature crystal that we use to compensate for temperature air inside the pressure crystal. And we do that with our calibration. So we harness a cut of quartz for that temperature crystal that we know is linear over the operational range of our device. We also utilize another sensor in our device, a reference sensor, and we have selected a type of cut of quartz for that reference sensor that is temperature inert, meaning that it has highest insensitivity to changes in temperature. It doesn't affect its frequency. And we did that because we want the reference frequency to stay the same no matter what. And so that's one interesting property of quartz, that it's anisotropic. Depending upon its orientation, it changes its sensitivity to temperature. But that's not the only thing that it changes its sensitivity to. It also changes its sensitivity to etching. So we talked about using hydrofluoric acid, and this is really a neat thing that you can do with quartz. If you were to take a sphere, it's very popular in certain spiritual or healing circles to create quartz spheres. They're beautiful pieces of art, but if you were to take that sphere and you were to stick it into a tank of hydrofluoric acid, the etching rates in different orientations are extremely different. And so over time, instead of that sphere just turning into a smaller sphere, which would happen in an isotropic material, the sphere will actually turn more into a triangle because the etching rate is so much different in the z-axis than it is in the x-axis. So you're going to see, the sides start to cave in while the x-axis is going to very slowly move in. And so that's another thing that's very different about quartz, is that it's anisotropic for etching. In addition to that, we talked about bulk devices earlier in the presentation, like the thickness shear mode resonator. We also have different quartz devices that harness different acoustical properties. Those are like the SAW devices. So depending upon the cut of quartz that you utilize, you can utilize those acoustic properties to get much higher frequencies. And lastly, another anisotropic property of quartz is the optics. There are certain cuts of quartz you could take, if you ever have a quartz ingot and see a show, you can take and you can look straight through it, and the light will not be polarized. But if you look across it, you can actually polarize light. And so depending upon the orientation in which you hold the quartz crystal, the optical properties of quartz are much different. And so that's something else. So at Quartz9, we understand the anisotropic properties of quartz. We understand the many different cuts of quartz crystals, and we utilize those in order to harness, depending upon the application that's required. So moving on, this is the other property of quartz that you could consider magical. And this one is where we talk about the physics. And I'm hoping that we all can understand this, and I'll explain it the way that it was explained to me. So we're familiar with what a tuning fork is and what it sounds like. And we've talked earlier about quartz being used as a tuning fork. One of the ways that we rate resonators, which are systems that once energy is put into them, they continue to move, is Q. A Q is a unitless metric because it's energy stored versus energy dissipated. So there's no units to Q, which I think makes it more complicated and more difficult to understand. But I think the important thing to think about is the illustration of a tuning fork. So if you have a tuning fork that has a very high Q, when you strike that tuning fork, you add energy into the system. That tuning fork is going to resonate for a very, very, very long time if it has a very high Q. And a very low Q tuning fork, you can strike and it will come to a stop much sooner. And so the way this was explained to me is we have certain tuning forks at Quartz9. These aren't quartz ones, these are actually metal ones that we use to demonstrate this principle. Is you strike it and it will resonate. I think we timed out for 3 minutes off of one single ding. And then we actually change the mass of the system. And by changing the mass, we distort the Q. And then when you hit it, it lasts maybe for 2 to 3 seconds. And when I say we change the mass, actually the only thing we do is we actually just move a tiny screw ever so slightly, just a couple threads, and we drastically change the Q. And what's interesting about quartz is naturally it has a very, very high Q. And there are things that we do at Quartzstein to increase the Q. So one of the ways to think about this is that a mechanical watch has a Q to it, because those are mechanical systems, and the Q to a mechanical watch is something in the realm of 100. That's, if you take the energy stored in a cycle versus the energy dissipated, it's around 100. When we talk about high Q for a quartz system, we're talking, Qs upward to a factor of 1,000,000. And so that's kind of the difference in quality. Now, a Q for a quartz resonator that's put into a watch, those have less of a higher, they don't have as high of a Q factor because they're less accurate. But if you're looking at the Q of a device that goes inside of an atomic clock, that's going to have an extremely high Q factor. I'm not talking about the cesium, and I'm talking about the control electronics. And the reason why is Q is a property that is in line with accuracy, because the higher the amount of energy stored versus dissipated, the less energy or interference that you need to infer with the oscillator. It can continue oscillating, which results in higher accuracy. But even utilizing Q, or even utilizing quartz with a high Q, there are many different factors within the quartz that change the Q. Things like surface finish, bonding and mounting stresses, the temperature, which we talked about earlier, any impurities. That's why synthetic quartz provides such high value versus a natural quartz. And then surrounding gases. If you resonate a tuning fork inside of an air-filled room versus a vacuum versus other gases, it's going to resonate differently and have different Q values. And so the science around harnessing Q is another part of Quartzstein's legacy, is that there's many different research efforts that have been done to optimize these different factors in order to increase the Q. So that's something that we've done as well. Lastly is the property of elasticity. And so this is a cross-section of a grossly exaggerated quartz pressure sensor. And so you can see here you have the bulk resonator in the middle, and then you have the shaped Jolly Ranchers. Again, this is a cross-section on both the top and the bottom. And all of that is bonded to form a single crystal. And the movement that you see, again, we move our resonator at 7.2 million times a second. And this is the last property of quartz that really makes it stand out, is its elasticity. And so quartz has the ability to be strained or compressed significantly compared to other materials, and yet still retain its original shape. And why this is important, I'll give you another just elementary example, is take an elastic band. Now take that elastic band and you stretch it as far as you can without breaking it, and then put it back down. If you look at that elastic band, it did not return to its original shape. There's a bias that's been created, or you've altered the shape of it by stretching it. This is where quartz stands out. You can significantly compress or strain quartz, and instead of looking different after it's been under that stress, it looks exactly the same. And so the movement that we have here, I want to point out, is extremely exaggerated in order to show what happens on a resonator. But the actual movement, so the actual resonating area, is actually on the order of tenths of angstroms. So physical displacement occurring on Quartzstein's resonators are really on the order of tenths of angstrom. So that is a gross exaggeration, but it does show the point that that's in the center of the resonator is where movement is occurring, where we are straining the quartz. And that strain never takes the quartz away from its original shape or size. As soon as the quartz resonator is shut off, it goes back to its null position or original position, and it is not altered. So with that, in summary, I just want to recap what we've talked about. Quartzstein uses synthetic quartz for its quartz sensors. That's lab grown. Quartz devices are used in all technical industries. I referred to it earlier as the salt of industry. And the reason that we utilize quartz as a precision sensor is due to the following properties. One, quartz is very happy being quartz. It's chemically inert with the exception of hydrofluoric acid. Two is it's incredibly robust and hard. It's ruggedized. It can take a beating and still keep on ticking. The third is probably the most important, which is the piezoelectric effect. If you induce, you squeeze it, you get a charge. If you put a charge onto it, it will physically displace. It's anisotropic. We harness the properties of quartz for the benefit of our application. There are many different cuts of quartz. You can read about many of them on Wikipedia, and there are some that have yet to be published. In addition, there's high quality factors, meaning that the energy stored in quartz is not dissipated quickly. And the very last is it's elastic, meaning that when we deform it, it goes back to its original position and is not deformed. So with that, I just want to open it up to Q&A.